Osama.
Hello. 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 Hello.
Hello, assalamu alaikum.
Fine. So, is my voice clear?
Yes, yes. Your voice is
Yeah.
clear.
Yeah. Thanks. Sorry for the delay.
No problem. We will be starting the webinar.
So, shall I present now?
Yeah, I will just give a start introduction, and then we can proceed further.
Yeah.
So, Assalamu alaikum everyone. This is Vida Fatma from Engineers Talk. Engineer Talk is an organization that aims to bridge the gap between student and professional life. So, welcome to our webinar, Industrial Scope of Semiconductors and its Research Gaps. So we have Dr. Fiona Rose, our esteemed speaker, with a lot of experience in the field of semiconductors and microelectronics. Dr. Rose, assalamu alaikum. I think your speaker is not working.
Oh, Walaikum salam. Yeah. Sorry. Yeah. So, good morning, everyone. So, today, I don't know how many of you are like from device background. I assume that like most of us you are like undergrads. So like it's like I'm just like giving a basic talk, very fundamental, related to semiconductor processes. So and like what are the like what is the like what are the scopes, and like how much wide is this field, like how much depth and width this field has. So just I would like to share my screen.
Oh.
Is it are you able to see?
It's not loaded yet. And from my side, Osama, can you confirm? Is it visible from your side?
Please let me know.
Just a minute. Oh, it just went away.
I think there's some connectivity issue, but my connection is fine.
Mm-hmm. Maybe there is a delay regarding that. Just a minute, let me check with Sama.
Are you able to see?
Actually, you can proceed the webinar. We will edit it
I
out.
will I will
Yeah,
share again. I will
yeah.
share again. Are you able to see my screen?
Just a minute. So actually, Dr. Imroz, we can edit it out later. We can edit the screen with it. You can continue the webinar.
Yeah,
I'll.
yeah, but like if the screen is not visible, then how I will present, right?
Uh,
So,
okay.
uh,
Then can you share the presentation with Osama? Maybe I can share it.
uh, like
if you don't mind.
okay, I can. Just I'll try to reconnect if it works. Just like maybe like it's the content is not publicly accessible. So
Oh,
I'll try
screen
to
is
rejoin
visible.
it.
For
Yeah.
majority, screen is visible.
Okay. Are you able to see?
No, I can't see it. Maybe there is problem in the connection side from my side. So screen is
Okay.
visible.
Fine. 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 Fine.
You can continue.
So okay. So very good morning. Sorry, it's I think it's afternoon there or like evening. So yeah.
Yeah, afternoon.
Yeah, very good afternoon to all of you. So I like I just wanted to present a very like very fundamental talk into like semiconductor device processing. Like I have done my PhD, particularly microelectronics fabrication, and right now what I'm doing, like it's mostly I'm working on a project in which we are collaborating with one of the leading foundry like uh, it's called Global Foundry, and like I characterize the industrial test devices and with some cryogenic temperatures, and I will be discussing in the later part of my talk. So so like the title of my talk is how sand is made to think. So we all know that semiconductors are usually they have certain band gap, and which is not very high compared to insulator, which is not very low similar to metals. So semiconductor, the beauty of the semiconductor is that uh, like we can tune their conductivity. So this is the best part of semiconductors, and I assume that most of you have might have gone through this kind of topics. I'll be, if it is very boring, please let me know. So like see, you can see like there is a very huge market of the semiconductors, like from starting from the memory, like we all know like these days SSD is being used. Like before that like flash memory have been used, and like the logic circuits, like of course the digital circuits, whatever, right? So everywhere, like you see, like these all are the application of semiconductors, starting from sensors, optoelectronics, analog electronics, digital signal processing. So it's a very huge market basically. And as you know that right now the whole world is having some kind of chip war or something, like it's kind of cold war, and every country want to make their own like own semiconductor foundry. Like previously TSMC in Taiwan is one of the major center of manufacturing chips, and like but now like US is also have some kind of act, and Europe is also having one of the some of its own chip act. So like everyone wants to become very independent in this field, like because it's the right now it's the need of the hour, right? So every kind of electronic equipment semiconductor is the basic thing, right? So from sand, basically sand is silicon dioxide, and from silicon dioxide it goes to several kind of processes, and after that we extract silicon wafers from there. So like uh, while fabricating semiconductor devices, like we use like a CAD, what you call computer aided design, like and clean rooms fabrication, and like packaging, and whatever you might have seen these things in some of your undergrad courses if you are in, and it's like very fundamental, and it's like it's a very big market, like billions of dollar market, as I've seen this slide to you. So so every country wants that they should have this thing own, they should have their own foundry, so that they can be independent. They need not to pay for the customs. For example, US didn't have any kind of foundry not much as compared to Taiwan, but they are also investing in that. So so like it goes to several kind of process, like there's multiple of process. I will be discussing very fundamental processes out of them. So integrated device manufacturers such as maker, one of the leading makers such as Intel, Samsung, they manufacture, their design, and they sell their chips. And there are some of the fabulous manufacturers such as Qualcomm and Nvidia. You know, all right, Qualcomm, like it's one of the leading mobile processor. Nvidia is leading in graphic processors, and they basically focus on design and not the manufacturing. They outsource from the foundry, and they give their design, what we call a tape out, and they give their tape out to companies such as TSMC, Global Foundry, UMC Singapore, and how this circle goes, right? So mainly TSMC is the leading one. Like it's right now, it has reached to up to 1 nanometer technology node. Like so, it's ultimate. Like they're the leading ones, right? Global Foundry, UMC. uh, uh, the VSI technology means like the transistors. Basically, I will be discussing. So it's a very basic building block of any kind of device, right? Either it is a digital device, maybe like a memory device which has which is mostly particularly digital, and it has no kind of moving parts, right? And it's kind of on chip brain, right? So it's but there also one of the more technology is called MEMS. This is also a microfabrication, but it is mostly related to sensing and part and which is having some movable parts. So basically both are having same kind of technology, like process flow. The MEMS market was around 15 billion, but the semiconductor market is around 420 billion. And it's like increasing day by. It was 2017, now it is 2023, and everywhere is just on to the same thing, right? This industry is basically running in parallel to the what you call data science, right? So it's the need of the hour, and many people are investing in this. So I think I should skip this. Okay. So see, so there is something called a technology team who focus on manufacturing these devices, and there is something called design team. So the technology team is just as I said, it's TSMC, Global Foundry, UMC, etc. And design team is like Qualcomm, Nvidia, ARM also is one of the leading company. So so they design, and they just they both work together, like in collaboration, and they just it's a circle, it's a cumulative circle, and they just they design thing, then they give them, then they fabricate, then they send to them, then they will get a feedback. If there is some improvement required, then they will again approach. Hello.
Sorry for interrupting. I think your screen is not visible for to the participants. Can you
Oh,
share it again?
I think it's some network issue.
Because
Just
many participants are saying that your screen is not visible.
yeah, just hold on.
I'm so sorry for the interruption.
I don't know how it is, like should be very flawless.
Mm-hmm.
Are you able to see my screen now?
Mm, yes.
Is it fine now?
Just a minute. Okay. Thank
Is
you.
it fine now?
Yeah,
Okay.
yeah.
So yeah, thank you. So yeah, as I was talking about, like there is a technology team and there is a design team, and they both work together. So if design team, they just send a tape out to the technology team, they fabricate and they give to them, then it's a feedback, and it's like runs like that. Once the full IC is optimized or the device is optimized, then it will be sold, sent to the commercial or marketing prospects. And it's like once you get a correct tape out, it's like it will be sent in sold in like billions of dollar, and it's amazing. So like, so technology for the like all know like iPhones, they are all using FinFET technology basically. And like Samsung is up to like 45 nanometer technology nodes, and 30 the iPhone is actually they have been using previously in iPhone 4 as some 45 nanometer technology node by Samsung, then in iPhone 5 just 34 nanometers. So these these 45, 32, these are basically gate length. Means it's like it's the name of the technology, but it is directly related to the gate length, or you can say the size of the transistors. So I assume that you all are aware of the transistors, right? So I will be discussing very shortly about the transistors also. So like I'm just explaining. So right now iPhone like 8 has been using 10 nanometer, like maybe in iPhone 10 I know that they have been using FinFET 8 up to around 3 4 nanometer technology node. So it's something called Moore's law. You might have you all might have been aware. Like as the year passes, the number of transistors on any kind of chip doubles. So that's all. But now, right now, Moore's law is saturating because people have already reached around 3 nanometer or 2 nanometer, right? So anyway, now like there's several other issues which have to be addressed, and industry is working on that. So it's a MOSFET. It's a one of the basic building block of any kind of integrated circuit. You might know these like from a undergrad course, there's a source, drain, and gate. Like, and we control the current through by applying the gate voltage, and these are some of the parameters like threshold voltage, on off current, current, and etc. So like it's one of the basic building block, and which is used to make which if you see any kind of microprocessor, Intel like Core i7 or something, maybe in like Apple's M1. So it will be having billions of transistors like this. So that's why the technology has to be evolved, so that we can make this device as shorter. So this is what the gate length I was talking about. People are trying to reduce more and more, and it has been reached up to around 1 nanometer also by TSMC. So like right now, so there are several other challenges in this device which industry is focusing to improve this device. So if this device is improved, then our full like circuit, integrated circuit, will also improve. So like it's just analogy of any kind of transistor. So it's like I also always treat current like a flow of water. So just like a tap, you control the flow of water using a tap. In similarly, in transistor you control the current through gate. So this is a similar kind of analogy. And there are like it's like there can be many much analogies in this like flow of water and the current flow. So this was the first very early MOSFET, it's called in 1980s. And this was in like it's called a single well CMOS process. So CMOS is something having complementary transistors. One is the N channel and the P channel. So on both transistors on the same substrate. That's called mono. This is called monolithic integration. So all of the devices in if in any integrated circuit you see, the substrate will be same, right? So substrate will be same, and all the transistors will be fabricated on the same substrate. So that's called something called monolithic integration. This is a single well process because one well is only used. So this is a twin well process. So since the technology is being evolved, so you can see in this case that there will be so much leakage, like bulk current will be flowing because there is a junction, right? this is the N well, P well. But if you see this process, the P well and P dope well is doped as well as N well is also doped. So if the doping has increased, then we will reduce the contact with the substrate more, like there will be less likely substrate current, and that contribute in the leakage. So like I assume like you might be aware of these facts, the leakage and all. So because basically in any transistor we just want that this current should flow, and any kind of other currents, like any current from the substrate or source to substrate or gate to substrate, it should not that has to be avoided. And for that reason all the people have been working in this area. So I will move quickly. And this is the modern day MOSFET. This was the very old MOSFET, like it's modern day which I am working. So it's called FDSO, fully depleted silicon insulator. So basically, we are separating the full device from the substrate, and there will be a buried oxide which avoids any kind of leakage or any communication from the substrate, and that is good for any transistors. And this is the FinFET technology, which is much improved technology, but like slightly complicated. So there is always competition between a FinFET and FDSI. Like FinFET is being used by Intel, Samsung, everyone is using, like Apple also in iPhone 10, I think FinFET was used. So these are some of the leading today's present day devices. Uh, Unlike the CMOS process, it's not the complementary one. So and this is one of the stacked nanosheet FET, and there's all also gate around FET. So many things are there in the. So technologies keeps evolving, because we have all kind of processes, like very costly equipment, and we can play with the process integration, right? So and this is called the wafer process flow. Several things are involved in this, like so many things, starting from the wafer which is obtained from the silicon dioxide, which I will be discussing very soon. And it goes through the thermal process that's called oxidation, then like photolithography, metallization, and then etching and dielectric deposition, and like CMP, that is chemical mechanical polishing. Like we want to make our substrate very flat with reduced roughness. And that once like and many things are involved in this, like photolithography is maybe you might have read in your undergrad course, like should be a science technology course, like it uses several mask, and mask has to be designed. And like just for your knowledge, I will say that the present day existing technologies such as FDSOI and FinFET, they have around like maybe 50-60 mask processors. It's very complicated. So they don't do for only one single device, they do for a very big wafers. And in one process they will be making some like some around thousand of chips, and each chip will having some billions of transistors. So you can understand how much precision is needed. So once the IC is fabricated, it goes to test and testing, and then packaging, then final test is done, and whatever I saw, like told you, so basically this design comes from the design team such as Qualcomm, Nvidia, and this all stuff is being done in the TSMC Global Foundry and etc other foundries. So why silicon is used making 90% of devices? It's like abundant. Coming to the very basic, it's very abundant. So there are also other options such as germanium or gallium oxide, but silicon is abundant. Allah Subhanahu wa Ta'ala has given so much sand, right? So it's abundant, and just it's very stable, it's inert, and it is very robust kind of material. uh, Maybe like there are some kind of limitations, but for very precise application, we don't use silicon. We use gallium arsenide and or some other silicon germanium alloy is also being used. So this is a very basic reaction, like from sand, how silicon dioxide converts to silicon, and we extract from this. So basically, this reaction is done in at very high temperature, and and this reaction is done in a separate kind of chamber. It's a separate process that's called float zone method. there will be your polysilicon rod, that's basically silicon dioxide, and we also give a seed crystal that is a very very pure silicon. So it rotates, and there will be heating coils, and slowly this, when this reaction starts to occur, slowly in the lower part silicon starts to build, and that's how we make our wafers by slicing this part. It's called an ingot. So there is another method, this called Caesar quasi Caesar method. This is similar to that, but like a different kind of arrangement. Where but always we need a single crystal silicon as a seed. So this crystal is very very pure silicon. So like a different arrangement. So there are like ways how which is efficient and all. Like you can read the literature. So this is, you can see it's this is called an ingot, and in the bottom part pure silicon is being poured. In whole part this is SiO2, because there will be seed crystal here. That I hope people can see my slide, right? Hello.
Yes, it is
Oh, okay.
visible.
Yeah. So the bottom part, most part is the single crystal silicon. Then this part will be pure silicon by this process. And once we dice this ingot, this called ingot, we dice it, and it gives a circular shape. So they make we for characterizing this, like we make a notch from where we we define it as the n type or p type or whatever I will discuss about that. They always make a notch to just as a reference point. This is called a die. So they are like multiple, they are 12-inch die, very bigger die. So you can see it's a ingot, right? So if you slice is in the upper part, it will be bigger wafer, from the lower part it will be small inch wafer. So standard is 12-inch, 4-inch, like that, 6-inch also. So the IC fabrication step, like how you fabricate in integrated circuit. So once you get a silicon wafer, so you do it goes to n number of process, and it's a very very complicated process. That's what all foundry are doing right now. So it's a very very hectic job, but it's a very interesting and exciting job as well. So like it goes through several kind of processes, such as as I just showed you that previous slide, like like first of all it goes through doping process using ion implantation or diffusion, etc., or like kind of if you want to deposit any fill using ALD, etc., CVD. Then we clean the wafer, like an etching process, CMP process, and annealing processes, annealing something when you do any kind of doping in any silicon wafer. So the for any kind of rearrangement you just heat it, so it naturally rearranges itself. And the last one is the patterning using photolithography, and it also involves several processes, like resist coating, then masking, and etc., exposure. So it's very complicated process. So all these things are done in a clean room. So clean room is something, it's very artificial environment. Many people of you might be aware of this thing. So all any kind of processes, semiconductor process is done in a clean room to avoid any kind of particle contamination. Particle contamination, like any dust particle, right? So if you see in any room, if a dust particle is around, maybe it will be around 50 micron size, right? But if we or like maybe less than, okay, you can say 10 micron size. But if that 10 micron particle sits on my transistor, and my transistor gate length is around 10 nanometer or 22 nanometer, so it will cover so many transistors, it will damage my full device. So that's why we need a very clean room. It's called a clean room, and it has very low particulate count, because in any kind of clean room environment, there are very regular filters working, and that solves the problem. And so it's this kind of clean room suit, we it's called a PPE also, you might have seen. So this is a clean room suit. It's like whatever cloth is made of, that is also very lint free, particle free. So there are several category of clean room, like class 1, class 10, class 100, class 1000. So means class 1000 means 10,000 means class mean 10,000 means like there will be 10,000 particles per feet cube. So you can imagine. So like one of the very sophisticated clay room will be class 1, obviously, or class M1. So like this things are done in any for any fabrication purpose. So first process for any kind of like dielectric formation, means gate oxide formation, is oxidation process. And like there are several ways to do this. Like one of the thing is we used to use in a kind of, it was a very long tube, and we just flow the oxygen through the tube, and we keep a wafer on. There will be some kind of slots like this, slots will be there. So and we flow and we control the flow. And with that flow, and we also they are kind of dry oxidation and wet oxidation also. So dry oxidation means that we don't introduce any kind of water, any kind of moisture. But for wet oxidation, we will introduce moisture, but it will be very fast, like more thickness if you want of any oxide layer over silicon dioxide, silicon wafer. So so you do wet oxidation. So basically, oxidation is a very very crucial process, because it forms the gate oxide, as you have seen this part. So this is the gate oxide, right? So it's a very very crucial, because a gate is isolated from this channel, and it just controls the current through the gate voltage, or the electric field. So it's very crucial that we have very good quality of oxide of over the silicon wafer. And they are thin film deposition. If you want to deposit any kind of metallization, for example source drain metal, or epitaxy. So epitaxy, like forming a very very thin layer over any kind of wafer. So that for example, if you see this FDSOI technology, so this is a very very thin layer over top. And this there will be a substrate similar to a silicon substrate. It will be very thick, and then we deposit in oxide. Then we deposit a very thin layer of, again, some thin layer of silicon, and that is very very pure, and that is called epitaxial layer. Over that we form this device. So it's this FDSI is very very efficient, in fact. So so there are ALD also. So ALD, like atomic layer deposition. So you deposit a thin layer of any material, like with some kind of precursor, and it forms like of the film by atom to atom, like layers by layers, at very precise condition, angstrom level, or electrochemical deposition. So the electrochemical deposition is for forming the interconnect. So it is basically the top part, how you interact, how your device is interacting from the outer world. So that is decided from the interconnect. So and this is the etch process. So like etching process. So whenever, like when you are fabricating any device, etching is very very crucial, because you don't want oxide to be everywhere, right? Once you oxidize your silicon wafer, you need to be that oxide to be removed from the source drain part. So you use there are multiple ways of etching, like dry etch. Dry etch is like based on plasma etching. So it like just you bombard your argon plasma, or maybe other kind of argon, or I think any kind of other inert helium plasma is also being used. So just you sputter, just like start firing balls on any surface, and just it etches. And like it's also like a very 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 costly process, but it's anisotropic. That means it etches in a single direction. But all other etching, such as wet etching, so wet etching is done using any chemical, such as HF. It's a very very dangerous chemical, in fact. And it's basically isotropic, like isotropic. So because it etches from the undercuts as well, so it forms something like this. So there are several ways, and some of the ways have advantages and disadvantages. But the dry etching is one of the very widely used for very precise etching. So I don't think like in present day technology the wet etching is being used, but for research purpose people are using. I have also used in my PhD, which very frequently the wet etching part, photolithography. So photolithography is basically patterning any kind of surface. So suppose you get a silicon wafer, and you want to deposit metal in some part, and we don't want to deposit metal in some other parts. So you need to mask the area, right? So the masking process is done using photolithography. So there is something called a photoresist, which is sensitive to light, and we expose the photoresist through a certain mask, and that will form our pattern, like how the pattern will be on the device, like how you want to form your source drain, etc. Basically this is the very crucial. This mask is the designed provided by the designers, Qualcomm, Nvidia, etc. So and it's like present day technology, there will be multiple mass process. Like you cannot achieve in a single mass process. So whenever you need to pattern, means you need to mask some area, you do photolithography, you deposit rays, you expose it, and then when you expose it, if it is a positive photoresist, the risk gets weakened, and you develop in some developer, and the resist part gets removed from that area which is exposed. There is also something called negative photoresist, when the exposed part become exposed part become more hardened, and other parts is easily to remove. So that's called negative photoresist. A typical microprocessor has around 50 masks. So you can because this is very old data. Right now people are doing very complicated processes. You cannot imagine, maybe 100 masks also. So even a single mistake in any of the step will be catastrophic for full process, and lead to lead to loss of like millions of dollars. Because you can understand how much precise this is. This is that's what I was telling, subtractive patterning. So whatever part is exposed, that becomes hard, and the other parts will removed. So as I was telling you, the effect of particle contamination. That's why we need clean room. Suppose you are like you want to you have made a photolithography, then you put ion beam. For this is ion beam is done for basically doping. So doping is something I means it's very common in undergrad. So doping is something when you tune the conductivity of your silicon. So silicon is basically intrinsic, but by adding some dopants, that means some impurities, you can increase the conductivity. So increase the everything, increase the decrease the band gap, increase the mobility, and so so basically for source you can see here. So for the substrate here, substrate will be intrinsic, but the source drain are doped basically, because they will be forming the channel. They are having this is kind of buckets of the carrier, and this is a base. So and just you need to tune the tune the channel using your gate voltage. And of course substrate is also having some of the magnetic carriers. So basically, whereas if your substrate is intrinsic, and if you want to make a n channel transistor, you dope using what you call phosphorus, n type impurity. And then in that case it will be n channel MOSFET. And if you want a p channel MOSFET, so you dope using boron, so it will be p plus and p plus. So that's how this doping is done using ion implantation. So yeah. So if you have done your lithography process, and if any particle sits there, it will be disastrous, right? So that's why we need clean room. So this is a typical CMOS process flow, because CMOS is very simple to understand. Means FDSY is super complicated. Even I don't work in foundry, so even maybe there are so many other processes. You can see here there are 19 or 20 steps for CMOS, and that is very old technology. No one uses CMOS right now. So it's like it starts from active trench isolation, that is like isolating all the devices, because we don't want devices to communicate. Then implants, that is what is called doping. Then there's something called VT adjustment is done, because usually when you go to lower channel length, you face something called short channel effects, and due to short channel effect your VT gets this called something called VT scalability, and VT increases. So you want to undo that thing using some halodoping, etc., oxidation. And so there are so many processes you can see. So this is a very interesting field to work on. Interesting industry. If anyone is interested, I was very excited to do device fabrication. That's why I did. I chose this thing in my PhD, but it's like very frustrating as well at the same time. So this can see it's a very conventional CMOS chip layer. So you can see at the bottom is the actual device, but at the top, how it communicates to the outer world, they involves several interconnects. This is called interconnects, and this is achieved through invention. And whatever IC you see in the market, that's just tip of the iceberg. Inside, so that's the package IC, and even this is not packaging. Packaging is done over this. So there are so many things involved either at the top part. So how you want your device to communicate, that depends on your interconnect. How you want your device to communicate to outer world, that depends on the interconnect. So this is a same image of the CMOS chip, CMOS device basically. Like you can see, like so much. These are the spacers, like isolating all the device. It's called shallow trench isolation. So I think this is a CMOS thing because it's a 200 nanometer. And so basically once you make a device, once you optimize this device, what do the circuit people do? Basically what do what how the device community, how TSMC communicates with Qualcomm or Nvidia. So that is something this. So like how we go to device to surface circuit. So that's what I'm doing. I'm working on this 22 FDSI device. I'm working on 22 nanometer channel load, and it's a FDSI device. So so like for whenever if any foundry makes any device, they make there is a existing model for that device, and they make a PDK. PDK is something, suppose you are making suppose any kind of foundry is making a new device, they will have everything about that device in terms of parameters. There are n number of parameters in any device. So how because for any circuit simulator, means basically Qualcomm is making a circuit, right? If they are making any application, any mobile processor, it's a circuit. So they don't know about the device, but they will contact the foundry, and foundry will give them some parameters. That's called process design kit. And those parameters are are for a particular model, that model is being used by the circuit community. So that for you, any circuit simulation, when if you might have done in your undergrad, you use like P spice or LT spice, the very basic simulator, circuit simulator. So when you use a transistor MOSFET in that particular circuit, so it needs a model. A very basic model is spice level model, which is like 50 years old model, like linear region. Like you can see here, this is a linear region, it's a saturation region. So this all these regions have equations. There is different equation for saturation region, and there is different equation linear region. So so these circuit design people, they come, they get the PDK values from the foundry, and then they plug those values in a particular model, which is also again made by some third number of people, that's called device modeling team. Like UC Berkeley has a very famous model called BSync model, and this that model is being like very widely in the academia as well in industry. But of course industry is having making their own model. So model is something like, it's a model, it's a set of equations which replicates a device behavior in any simulator. So because if any circuit designer wants to design any circuit, he cannot he wants to simulate, right? So for simulation he needs the analytical description of any device, and that is something called that is nothing but a set of equations which replicates the device behavior. Because if they do not do that like this, and just they keep doing hit and trial, because they want to send the final final circuit to the foundry. that's called tape out. They cannot play with that, so they whatever modification they do in their circuit, that they do in the simulators. So it's very very important part of the whole industry, that the model should be very very accurate with respect to a particular application. And this is called PDK development. So how do you develop a PDK, how basically foundry develop PDK, and what I am doing in my a job here in University of Glasgow. So we measure the data. If you want to build any new PDK for any particular temperature, because I am dealing with cryogenic temperatures, which is less than 100 Kelvin, 77 Kelvin, 4 Kelvin, or milli Kelvin even. So we measure the data at particular temperature, then we extract the model parameters for from that particular measured data, if the data is reliable. And if the data is not reliable, then we gain more confidence using over my data with using TCAT simulation. It's a numerical simulation. You can Google it also, or you might be know, some of you might be know aware of this thing. And then you understand the physics of the device, and then again you generate the IV curve from the TCAT, because TCAT is the circuit people do circuit simulation. TCAT is basically device simulation. So in TCAT you can do the everything whatever foundry is doing in the software. So starting from the process, you fabricate the device in the TCAD, then you characterize the device, means you apply the bias and you study the device physics. So whatever foundry is doing, you can do actually in the TCAD, and you can study about the physics, because foundry is just fabricating a device. But in TCAD you can study everything about the device, like how the carriers are flowing, how the channel is forming, whatever what changes you need to improve the VT, etc., etc. And sometimes the TCAD simulation doesn't converges at, if you suppose for me, my case, I want to develop a PDK at 4 Kelvin, and at 4 Kelvin these because TCAD also has several models. Those are numerical models. They work on very Maxwell equations, etc., very fundamental electrostatics, and they won't convert. Those models are made for room temperature particularly. But when we go to lower temperatures, what I'm doing, so then we can also, there is an alternative way. We can make a model in Verilog A. It's called compact modeling. So it's completely like a kind of empirical model, just to replicate your device performance, etc. So you can Google all this stuff, like it's very very exciting. And this is what the industry is doing. And this is where so much career scope and jobs are lying, if you can work on this thing, because this is the best market right now for semiconductor industry. Because the circuit designer will need accurate models, and if you can, because this is my field basically. So that's why I'm more excited about this field. And what I am doing, just to show you here in University of Glasgow. So basically we have this called a dilution refrigerator. And it has so it has several plates, and every plate it has works is at a different temperature, starting from 50 Kelvin to 10 millikelvin. Because for quantum computer application, so it's unlikely from the classical computation. It's not binary 0 or 1, and it's a qubit. So qubits basically are made of superconductors, and they work at very very low temperature. So in order to drive the qubit, we need some kind of circuitry, and that circuit won't work at this much low temperature. So that's what I am trying to make, like collaborating with the modeling team, to make more and more accurate models that will work at low temperature, so that this quantum computer which looks very very big now, it won't be this much. It can be like, it's very early stage of quantum computer. Means if you just Google quantum computer, you will see very very big fridges like that. So many lines will be there. So yeah, so that's all. Like just I wanted to explain, give you a brief introduction of this kind of field. And so there are a lot of career opportunities in this field, like from the device aspect, like for the foundry people who are making fabricating devices, and then material people, because material study is also very important, like to to make new alloys like silicon germanium is being used, because silicon is having slightly lesser mobility compared to germanium. So you tune the mobility by making alloy, and so many stuff is going on. So all these people fields are interrelated. Then device modeling, as I said you. Then characterization is something measuring your device. Like when the foundry have made the device, they make some kind of test devices on a particular die, and then we need to characterize, and that's what I am also doing here. And this is the design team. So the design team make they they do the simulation, then they make a tape out like this. And like what opportunities in quantum computing hardware. So there are so many opportunities in the area if you try to explore, and it's a very as to be frank, I would say, if you have expertise in any of these area, you will have a very bright future, particularly in one of the developing countries like US, who is very much interested in investing in this area, because they want to become independent for this, right? From like foundry. They don't want that foundry to exist in particular part of world. Like, they want everything from their themselves itself. So yeah, thank you. Questions, any questions? I
Thank you.
hope you are not sleeping.
Thank you so much, Dr. Imrose, and we are open for questions just in case if anyone have questions, feel free to ask. I don't think there are any questions as the topic was very broad and it had a lot of subtopics, a lot of things to research about, which is more like an open topic as compared to rather having questions. They are curious that they will need to search more about it before asking the right question.
No, but
So
I don't think like they should not ask any technical question. They can ask from the career prospect also, if they are interested, like what to study, how to go. Like that is, I am open to answer all kind of questions, especially related to career, because I assume that most of them are in undergrads and they need some direction, and this is one of the very cutting edge field to work on.
mhm. Okay, so someone is asking global foundries kya hai?
So
What is
Global Foundry is a company who fabricates devices, just who have the full fabrication facility. As I showed you, they have the clean rooms and everything. They do have a device modeling team and device engineering team. So they engineer a device, then they fabricate in their foundry, and they accept the tape out from the other design people, the circuit people, and they fabricate for them also. So you can Google Global Foundry is one of the leading company.
okay, okay. Thank you. Anything else? In semiconductor industry, where does the India stand?
So India, I don't think so much, because they don't have any foundry as of now till date. It's just going at the university level at a very small scale. So at the research level, so from the research aspect, they are very sound. Means from the fundamental aspect, they are being taught everything. And in the labs, like one of the leading institute in IITs, they have fab labs like this, as I showed you, clean rooms. And they just do what they don't do any commercial prospect, or just on the research level. But right now I think India is going to invest in fabs also. But they do have a very strong like whatever the device modeling part or device engineering part or the circuit design part, because although these things don't need any kind of facility, that they just need a computer and a software and a very like a good processor, that's all. So so whatever whichever like offices you see in the Silicon Valley, like Intel and TSMC, Global Foundry, and Samsung, every office is there in India as well, but they work in the back end part, or what we call the device engineering part or the designing part. So they do the back end part, but like they do go to US also to do any kind of experimental part. But that's how is the situation right now.
So are the opportunities only present in USA currently?
No, so as told that US is like they want like everything should be in US, right? But right now, there are a lot of opportunities in Taiwan, as that TSMC is better than any of the uh, all the companies, because TSMC are the leading company in device engineering. So TSMC in Taiwan, and like in Singapore, and like South Korea as well. So these in these some of the countries you will get lot of opportunity, particularly in Singapore, Taiwan, if you, and Malaysia as well, because Malaysia has a very big fab from Intel. So it's just wherever the space is available, they Intel wants to bring the fab and they want to build the fab. So that's how, like, right now space crisis is there. So like in US, I don't think there are much opportunities in semiconductor in UK, because they don't have much fabs like Taiwan and US. So it's like it's kind of limited. So that's why the Chip Act has come. You might heard about the in the news that US has a new Chip Act. So that act is made to build the foundry in US itself. Even US didn't have much foundries. So the main foundry was located in Taiwan and Singapore and Malaysia, etc.
Right. Okay. So anything else? I don't think so. There are any questions. Thank you so much, Mr. Ambrose. Uh, there's another question that जो opportunities हैं are the limited, like the mean future में, because I know it's a like booming industry, लेकिन it's only booming in the countries that want to open the semiconductor, like for example USA, that want to go in that apart from Taiwan वगैरह. So are these like the countries, for example Pakistan, India, are there going to be opportunities here in the future? What do you see, think
So
about that?
I cannot say that, because that all depends on the people who rule the country. That if they want to bring the investment, because if they will bring any kind of investment there, then they need the manpower. They need the right skill also. If the right skill, the skillful people are not there, because this is very precise and costly industry. You can see there are so many sophisticated instruments. They will be in billions of pound, like 10 billion pound or something like that. So it's very very costly. You cannot give to any kind of person, right? You need the right skillful people. And so that's how it goes. Like if you cannot take risk, and there is risk of life also involved in any kind of foundry. So you need very very skillful people for this kind of job, and it's very very like long process. Like it's a very long process. Like uh, it's very like hectic work as well. So it all depends on the people who rule the country, like they are interested or not, because it's very costly. If that doesn't goes, then it will be loss of lot of money, right?
So
So
for example, yeah,
yeah.
yeah, continue, sorry.
So I would say, like, if anyone is interested, so first of all they should try to like orient their career. Maybe they can pursue masters in electrical engineering or microelectronics. Then like they should try to acquire right skills or right fundamental knowledge. Skills, I don't say skills, because skills you can gain only in the industry. So first work on your fundamentals, like very very basic topics in you study in undergrad, like in electronics undergrad, like semiconductor device physics, wheel technology part, and many things, most transfer you try to give your. Then you try to apply in one of the good leading universities across the world in this particularly in electrical. You can try to apply. Then you can do your project in some similar, because if you apply in one of the good universities, they will be having such kind of fab labs for the research purpose. and you can get a relevant experience, then you can apply directly in the industry.
Okay. Because this is a very precise industry, so you can't enter the industry without experience or without doing the
Yeah,
master.
exactly, yeah, exactly. You need some kind of fab experience at the your study like research level as well. Even like peer people after PhD are so many people from after doing PhD are going in the industry, because in PhD they do gain lot of experience in the fab in the university level.
तो हम लोग क्या लैब्स इससे रिलेटेड नहीं है, लाइक इन पाकिस्तान और इंडिया द लैब्स आर नॉट प्रेजेंट.
uh, because lab is also needs funding, lot of funding, right? Because to buy a silicon wafer itself very costly, right? It will around maybe I think it around maybe 100 pounds for one wafer, so it's very costly, right? So we can so they need funding, so for funding they need some new idea, because if any kind of people is any kind of guy is investing in some kind of thing, any company is investing to agreeing to give you fund, they want some commercial aspect, because everything is business at the end of the day. This is all a business, the end product is the market. And if any anything is not promising for the market, it doesn't go, no one will fund you. Like you might see this Shark Tank and all, right? They will be interested only that if it's a promising thing and you have a right plan to do. So if you don't succeed, it is a loss of money. So it's better to like try to pursue your masters in one of the leading institutions in across the world, and try to gain experience from the every one of the leading institutions might certainly have fab labs and for the research purpose, and you gain that experience. Or if you don't want to go in fab, you can also go in the device engineering side also. As I explained you in the TCAD simulation, it's a very big. TCAD is very itself a fab, because everything you can do numerically there, and it's required, because nothing not everything can be done in the fab, because it's another kind of like safety check. If you do in the TCAD, you study over the device, then finally you can fabricate that device.
Right. Thank you so much, Mr. Ambrose. The session was
Yeah.
really helpful. The introduction was really necessary. We need to talk about, we need to have these kind of seminars so that people can get aware about these. Of course, if we don't discuss this, people are not gonna pursue it. They don't even know about it sometimes. So these kind of awareness are really necessary. So thank you so much for your time.
Mhm.
I'm so grateful that you attended the seminar to provide the nation, and I would love to have another seminar with you. Engineers team want to have another seminar related to the event in continuation with the seminar. So thank you so much for
Yeah,
attending.
thank you. Thank you.
Okay.
Okay.